Are you ready, kids?
Aye, aye, Captain.
I can't hear you.
Aye, aye, Captain.
Oh, this is a lesson 5-7, graphical definite integrals. Today's date is Thursday, November 21st, 11:21. It is my son's second birthday. Happy birthday, Riley. So we just need to calculate definite integrals, but now graphically. So yesterday we did it analytically, today graphically. Let's see what it even looks like. So when I see this function, I graph the function 2. That's it. So y equals 2. This is the function. You can even write it down. This is y equals 2, essentially. Y equals 2. So y equals 2, go ahead and show me what that looks like with your arm. Y equals 2, is that like that? That? Is it slope of 2? Yes, it's a horizontal line that goes through 2. Go ahead and graph it. Okay, but what does this even mean now? So I've graphed it, but the integral, and this is why these fields were unrelated for so long, the integral is the area beneath or between the x-axis and the curve. And this is, I say curve, it just means the function, right? So anything in between here and here is the area, but specifically between the x coordinates 0 and 3.
And
So,
then is that like the total surface area? So it's like 2 times 3.
Exactly. So go ahead and make another line over here from 0 to 3. So from 0 to 3. And it's like, okay, well, we have passed geometry, theoretically. We know how to find an area of a rectangle. I think this is like 6th grade at this point. 3 times 2, well, this is an area clearly of 6. That seems pretty straightforward, right? And it is kind of that straightforward, but I want to explain more what's happening in the background. I don't get that opportunity very often. So this 2dx, this is the area of a rectangle. And you might be thinking, well, what's happening with that d of x? I can finally explain it to you today. This is the area of a rectangle. Write it down. Area of a rectangle. So if I did this analytically, I'm going to move this y equals 2 to the graph. I know you don't have that technology, but I do. If I did this analytically, I'd say, okay, antiderivative of 2dx is shouted out. Oh, dear God. What is the antiderivative of 2?
It's 0, right? 2x.
2x.
It's 2x.
2x, because if I take the derivative of 2x, it turns it back into 2, right? I'm going backwards. So 2x and then evaluation bar between 0 and 3, and then I plug those in, and it's going to be, plug in 3, it's going to be 2 times 3, minus, and then I plug in 0, 2 times 0, and then you say, okay, well, that's going to be 6 minus 0, which is just 6. Okay, so analytically, it matches up, right?
Yes.
The graph matches the stuff that we were doing yesterday. By the way, this integral symbol, it means sum, and I get to explain why that happens also. So you can write over here the word sum. This looks like an S. It's because it comes from the word sum. Gio, stop playing with the ruler, please. And before I talk about the d of x and where this area actually comes from, I also want to point out that this was a positive 6. You can get a negative area. It's a positive 6. We'll say positive because above the x-axis. All right, so I don't have very much room. I'm going to. Do you guys have room like right down here for me to explain a little bit? Go ahead and draw a very, very skinny rectangle. I'm going to make my rectangle sure black. Your rectangle should look like that, ish. And I'm realizing that I can't cut into the space down here because we'll need some space to do some analytic analysis. But what I'm really doing whenever I'm finding the area beneath the curve, curves are hard. The reason that calculus was invented was to find math behind curves, specifically about how planets moved. So how do you find an area that has maybe, instead of a line here, some sort of curve? And the answer is, well, if I break this into infinitely many tiny rectangles, and then I add up the area of each of those rectangles, then it will get really close. It'll still have some error, but it'll get really, really close to the actual error, or to the actual area. So, and again, this is like the Calculus 101. The first lesson we ever went through when I was in calculus was Riemann sums. I don't even really get to talk about that in this class. But Riemann sums are a fancy way of saying add infinitely many, infinitely small rectangles. This distance right here is d of x. D of x meaning what is the change in x from the last rectangle? The delta x. I mean, back in the old times, this was called delta x. And that's still kind of correct, and you might see that notation on an AP Calculus test. I mean, I saw it in like 1998 or whatever. They called it delta x because the change in x. How much did you change in x for each of those intervals? Well, what if we say, let's change in x, let's take the limit as that approaches 0, which means you basically have no width. You're allowed to do that because we have limits. We have a formal way of doing this. And then, of course, what is the height? Height is just f of x, right? A general way of saying f of x.
Is this one of the lessons I had to teach last week?
I don't think so.
I think I have to teach a more Riemann sum. When did we have to teach lessons?
So literally what we're saying whenever we take the integral of f of x dx is we're saying what is the area of the sum, this integral, the sum of an infinite number of rectangles. So every time that you see just a general, oh, it's just a rectangle, you should be thinking, no, that is an infinitely many tiny little rectangles behind that 6, or behind this little shape.
Which makes more sense when it's a curve.
Yeah, and when it's a line, it's super easy. It's a rectangle. You just base times height. When it gets curvy, then it becomes harder. All right, so we kind of have the understanding of where that d of x comes from. It's the width, but that width basically goes to 0. It basically disappears as I take the limit as I approach, or as d of x approaches 0. I'll have an illustration up maybe after we finish this. Let's try another one. Go ahead and graph -3. Y equals -3. What does it look like? Everyone show me with your hands, with your arms too. Where's -3? Is it a slope of -3? There it is. It's horizontal. Yes. It's down here at -3. Okay, between where and where? Between 1, let's change colors here. How do I know it's between 1 and 4? Someone answer it.
Because the bounds.
Oh,
yeah.
Between 1 and 4. And before we even do the analytic operation, we know that the area must be, no, -9. This area here is -9. And I try to circle the area because sometimes you'll be adding like notation like, oh, well, this was 2.5 in the x direction and then maybe 3.1 in the y direction. So if you circle, it's like, oh, circles mean that it's area. Let's go ahead and solve this analytically. Antiderivative of -3, shout it out. -3x, and evaluation bar between, oh, it's not x.
D.
T. Whatever that letter is right there. 3t. Evaluation bar between 1 and 4. So I plug in, I still have -3 times 4, and I subtract -3 times 1. I have a double negative there, so whenever those negatives kiss, or whenever they touch, however you prefer the term, they turn into positive, so it's going to be a -12 and a 3, which is a -9. Hey, check that out, -9. And go ahead and write down, you already wrote it up before, but this is negative because why? Negative. Write down what Gio just said, yep, negative because, or Sego and Gio both said at the same time. He was louder. I hear people that are louder. That's how sound works.
Yesterday?
What happened yesterday?
I shouldn't say it over the recording.
Oh, okay. We'll say it off camera. All right, and I've already said this once, but I'll say it again and I'll write it down. The integral is the area between the function and the x-axis. And I want you to be impressed. I want you to be puzzled. I want you to think back in time to when Isaac Newton was saying, okay, if I take the derivative, that's the slope of a line. So if I have some sort of curve, I have the slope of the line. And if I go and I take the integral, I have the area under the line. Those seem like unrelated things, at least to me. When you first look at it, you're like, yeah, those are totally two different fields of calculus. One is finding area, the other one's finding slope. Like, one's geometry, one's algebra. Like, they're not even related fields. So how are those two related? The fundamental theorem of calculus says one's going forwards, one's going backwards. It's kind of this mind-blowing thing. These two fields of calculus are the same. They're calculus. It's a really weird thing to think about slopes going forwards and area going backwards, but that's how calculus works. Whenever you're you're deriving these equations over here in physics, and you're like, where are these formulas coming from? They all come from one basic force, gravity, right? Gravity is just acceleration. You take the integral, then you get velocity. Take the integral again, you get position. You know how to do that. You can actually derive almost everything that you have just with the knowledge that you've gained in my class thus far. You know gravity is negative 32. It's a constant amount. If I take the integral, negative 32t. Take the integral again, negative 32t squared divided by 2, negative 16t squared. Where do those come from? They come from calculus. Well, actually, you guys don't use feet per second, right? Use negative 9.81, use meters per second. I guess so. Let's talk about integration of a linear function. We did constant functions up here, so they were nice flat lines. Let's go ahead and graph y equals 2x. How does y equals 2x look like? Here's x, there's 2x.
Wait, here's my.
that works. It has a y-intercept of 0, and it has a slope of 2, which means right one up 2. There it is. So there's my function. And it's between where and where? Between 0 and 2. So your triangle. Oh, that is not a line.
Wait, but they're never.
So
like,
now we don't have.
They can be, but there's like tiny little. Yeah.
There's tiny little air, right?
That means that nothing is ever a straight line because that means they're all like.
So you are making the argument. So Claire, it sounds like you're making the argument right now that when we take the integral, it's going to be an approximation.
Yeah, it is an approximation because there's always going to be a small amount of air between it because if it's a slope, there can't be a straight line.
If you are limited to simply pre-calculus when you're not allowed to talk about infinity, you are correct.
Yes.
Now we can have an infinite number of rectangles, which has infinite precision, which means we have zero
But
error.
the line also has infinite precision, which means that infinite rectangles have there's also an infinite amount.
One day after school, Claire, maybe even today, please come after. I want to prove to you that these are perfect using Riemann sums. I will derive a Riemann sum with you, and I'll say, okay, let's take the limit as n approaches infinity. You're like, oh yeah, now we have, it'll be mind-blowing. I can even show you a computer application that shows you what happens in terms of the area. But when you take the limit as n approaches infinity, it is exact. It is no longer an approximation because it's an integral, no longer a Riemann sum. I kind of skipped over it because we don't have time and it's worth like hardly any points on the AP test. That's just the way that I'm gamifying this. So what is the area of this triangle? Triangles are what times what times what? Yeah, all right, so maybe you should have that off to the side. Area of a triangle, base times height over 2. We know that. So base here is 2, height here is 4. If you ever think that you're going to struggle with triangles, make it into a rectangle and then just divide by 2. The rectangle here is 2 by 4, which is 8. Then divide it by 2. Therefore, the area here, shout it out, is 4. And circle that on the inside. The area there was 4. Again, this is really composed of an infinite number of these tiny little rectangles. The rectangles that have basically no width, but they have a height. So let's go ahead and do this analytically. Let's test this out. Antiderivative of 2x, go. Is x squared, because it goes x to the power of 2 divided down by 2. The 2's cancel out, and I'm left with x squared. Evaluation bar between 0 and 2. Moving along very nicely here. Geo, plug them in for us.
2 part of 2 to the power of 2 minus 2.
Minus, you're plugging in this one now.
Oh, 0 to the power of 2.
Sego, simplify. 4 minus 0, which is 4. Hey, we got the same answer. Good on us. Again, we should label this as the equation y is equal to 2x. So far, so good. Let's move on to the back.
Where's it back?
All right, example number 2.
Is it the same thing?
Very similar. Yeah, go ahead and try this one. You guys got this.
We don't know
T is like x. This is no longer the x coordinate or the x axis. This is the t axis.
Oh, even though it's
Yep, it's a little pew. I'll
We
go ahead and
would
graph it
have
up here.
the one is oh.
Pew. There it is. And between where and where? Ooh, that's a little bit trickier. Between 1 and 3. So 3 is right there. 1 is right there. Which means if I'm looking at the area, you don't have to shade it in. You can do lines to shade it in to make it pop out more if you would like, but it does make it kind of harder to label. That is the area that I'm looking for. Not this tiny triangle. This area is not included either. Just that shape right here. This is called a trapezoid. Why is it called a trapezoid?
trap.
Yeah, because zoids are attracted to one
No,
parallel
No,
lines.
no,
No,
no.
it's a trap because you think you can solve it like a
So
square,
you
but
think
you can't solve it like
trapezoid.
What is the definition of a trapezoid? Prove to me that I taught you something in geometry.
I didn't. Did I have geometry with you?
Yes.
No, it's trapezoids. Zoids like one parallel
It's
line.
between two parallel lines and two unparalleled.
Pizza.
That's the definition. 2 parallel lines, there they are, and 2 non-parallel lines, there they are. All right, so you guys can use one of 3 formulas. Choose whatever's easiest. You can use the formula for a trapezoid. I don't recommend it. It's one more thing that you have to memorize, and you've already memorized enough. But if you want it, here's the formula for a trapezoid. It is base 1 plus base 2, all of this divided by 2 times height. Think of this as the average of the bases. This base is 1. This base is 3. Add them together. 1 plus 3 is 4. Take the average of 1 and 3, divide by 2. Essentially, 4 divided by 2 is 2. The average of 1 and 3 is 2. Then multiply that by the height. The height here is 2. 2 times 2 is 4. So the area here is 4. That's the hard formula that I don't want you to use.
I say we split it up into a rectangle and a triangle and solve it.
That is the way you should always do it. This rectangle down here is 2 by 1, which is 2. This triangle is 2 by 2, so 2 times 2 is 4, and then divide by 2, you get 2 again. And that's another way to get 4. If you circle them, you know you need to add them up, right? Always break them up, or you could use the fancy-pantsy formula. Again, solve it analytically. Show me that you know how to take the definite integral. Stego, t becomes t squared over 2, evaluation bar between 1 and 3. Arrow, plug it in. Careful. 3, you plug all of it in, right? 3 squared over 2 minus.
No, oh yeah. Minus 1 squared is 2.
Simplify, arrow, go.
9 over 2 minus 1 over 2. Which would be 4.
Cool. So we got 4 both ways. All right. And then finally, integration of a piecewise graph. And I noticed that this P got cut off. That annoys me. Piecewise graphs, essentially what I'm always going to be making you do is just find the area only graphically. There's no analytic that you need to do. Normally. The harder questions, I'll make you do it a little bit analytically. Like, how do I know exactly what the bounds are? You'll see something like that. Anyway, let's go ahead and break this up between 0 and 5. Mark between 0 and 5. Make your lines. So 0 is obviously right there. 5 is over here. This one's going to be between -2 and 3. You can do that right now if you want as well. Between -2 and 3. And then we have to split this up. So I'm seeing a triangle. I could do a triangle like that. There's a bunch of different ways to split this one up, right? I could have split it up like that. I could have also just split it up like this. Whatever way makes sense to you. This way is the one that I saw first. And then find the area of each of those segments. So the area of, I'm not worried about this segment because it starts at 0. It starts right here. So the area of that square, 1 times 1 is 1. Geo, area of this triangle, find it.
1.
Good. Claire, area of this rectangle.
12.
12. It's 4 by 3. Continuing, okay, let's add them all together. 12 plus 1 plus 1 is,
14.
woohoo, we found it, 14. Box it. Arrow, find this area of this triangle. It is indeed 2. Circle if it's an area. What is the area of this triangle, Claire?
2.
No.
-2.
-2. Good. The area of this triangle, Stego. Careful. It's 1 by 1. So 1 times 1 is? Divided by 2 is? 1/2. Is it positive or negative 1/2? All right, so let's add them all together. 2 and -2, they cancel each other out. The answer here is just 1/2.
I think I'm gonna have trouble making triangles.
Dividing up the shapes, is that the hard part? Okay, we'll just get better at it. That means I should probably spend more time in my geometry class because there is a whole like 2 units or 2 lessons devoted to dividing up shapes like this. Yeah.
Wasn't our geometry class the one where it was like half pre-calc?
You did pre-calculus and algebra 2 at the same time with Ben, Arrow,
No, I didn't do.
and Anya.
I did algebra
No,
2 in
that
8th grade though.
Yeah, and I was here when you were.
I
doing
didn't
geometry.
take algebra with you. I took that with
You
Miss
did it
Liz.
freshman year.
Anyway, that is the end of the notes. Thank you for watching.